Hello everyone, this is the third lecture in this course. In today's lecture, we'll be discussing how we can find the solution of the system, which is defined in the state space form in terms of state transition matrix. State transition matrix is a very powerful um, term, which actually finds the solution of the system from any initial time to any final time. It can be any value. And also it separates the internal dynamics of the system from the influence of the external inputs. So this is very, very powerful term, and where we can study the long-term behavior of the system. And also we'll find the solution both in scalar and vector case. It means first we'll take the scalar system, we find the solution, which will be followed by the finding the solution of the state, so the system which is defined in the state space form. So let's start the lecture. First, we'll take the scalar system and we'll find the solution of the scalar system. So these are the topics we go cover in today's lecture. So here, let's start with the system. We have the system, scalar system, x dot equal to axt plus but. And this is, let me define this equation number one. And this is scalar system. And here, let us find the solution for t greater than t. So t naught we can assume the initial point time value, and t can be any value. And here, what we're going to do is, also let us assume the initial state starting from t naught, which is denoted as x naught. Now, if you multiply both sides, equation one by the term multiplying both sides of equation one by e to the power minus a t minus t naught, we get e minus a t minus t naught x dot of t minus e to the power minus a t minus t naught a x of t equal to e to the power minus a t minus t naught d u of t. Let us define this equation number 2. Now, let's work on this part. How we can simplify this term. Let's say this term also you can write d dt e to the minus a t minus t naught x of t, we can write e to the minus a t minus t naught x dot t minus a e to the minus a t t naught x of t. So if you notice here, both this term and this term are same. So instead of this term, we can write this expression there. So now we can write from equation 2, we can write t dt e to the minus a t minus t naught x of t equal to e to the minus a t minus t naught b e of t. It should be noted that in most of the aerospace application, we assume most of the aerospace application, you can say flight application, we assume T naught to 0. So in this particular case, let me define this equation number 3. Equation 3 get reduced to d dt. We can write it to the minus a t x of t equal to e to the power minus a t b u t. We can write. Let us define this equation number 4. Now, if we apply the convolution theorem to this equation number 4, we can write from this equation, if you integrate equation 4 from t equal to 0 to t, we can write e to the power minus at x of t minus x naught equal to, we can write 0 to t. So we need to change that a tau instead of t, we can write tau because tau will be the variable of the generation, and b u of tau will be tau. Or we can write from this expression x of t equal to or e to the power minus at equal to, we can write x naught plus 0 to t e to the minus a tau b u tau d tau. Or we can write x of t equal to the power for 80 x naught plus 0 to t if the 80 minus tau a tau b u tau theta. So this is very, very important solution of the differential equation, what you have considered. This is the solution for t equal to 0, initial condition to t. So this is the equation number 5. So if you look closely this equation, this term actually talks about the natural system behavior. Because here, if you notice here, we can assume this is the term coming due to the natural dynamics, and this is the term due to the control input for the scalar system. So the solution of this equation of xt, this is talks about the natural system behavior, and this is talks about the how the external input going to behave the system over time. So we can say, so here this integral term talks about how the system will be behaved in the steady state. So we can write here the integral term talks about the system behavior at steady state. And this term, we can say, it is more how the system is going to go through the transient behavior. So this is how we can find the solution of the scalar system. Now let's extend, since we are going to deal with the state space system, so now let's find how can we find the solution of the state space equation. So let's work on that. Now, let us assume if the system is defined as x dot t a of xt plus b ut. So this is the state space equation. So here, one thing, this is the vector, this is matrix, this is the vector, this is also matrix, this is the vector. So this system is defined in state space form. Now we'll find the solution of this state space equation. This is the main goal of this lecture. How we can find the solution of the system which is defined in the state space form. So now, first let's consider, since the system is quite complex because the control input also in terms of the vector. So first let's go with the without influence of the control input, how we can find the solution of the natural system. So let's work on this. Without the influence of control input, let us define this the equation number 1. Without the influence of control input, we can write the equation 1, x dot t equal to a x t. Now, if we apply Taylor's series for the xt expression, we can write, but Taylor's series also is sometimes called power series. The power series, assume that the power series of x of t can write, so it is actually should be capital X of t, we can write in terms of power series b naught b1t b2t squared the dot bk tk dot. Let us define this equation number 2. So one thing here, b0, b1, b2, these are the vectors because the dimension of x and dimension of b2, b0, b1, b2 are same. So this is also vector. So now, if you substitute the equation number 2 in equation, this is, let me define this equation number 2. This is equation number 3. Now, if you substitute equation number 3 in equation 2, we can take the time derivative of the equation 3. So we will have b1 plus 2 b2 t plus 3 b3 t squared dot plus k bk t k minus 1 dot equal to, we can write a of xt. So a, we can write this full expression here, this expression here. So we can write b naught plus b1t b2t squared dot plus bk tk. So we can write it this way. Now, if you compare both sides, the power of t's, we can write from this. If you compare the power of t's, both sides, we can have these equalities. We can write b1 equal to a b naught, b1 equal to a b naught, we can write. And similarly, we can write b2 half a b1. So in place of b1, we can write a b naught. So half a square b naught. And b3, we can write 1/3 a b2. And in place of b2, we can write half a square b naught. So we'll have 1/3 into 2 a cube b naught. So we can go till bk equal to, we can write 1/a factorial ak b naught. So this is the equalities we are getting from equation number. Let me define this equation number 4 from equation 4. And so now also we can put, since we are going to del t equal to 0 for this particular case, so we can write in equation 2, if you put t equal to 0, so also we can write for equation, now we'll put a t equal to 0 in equation 3 and find the initial value of the state t equal to 0. So let's say at t equal to 0 from equation 3 we can write x naught equal to b naught equal to b. Now, if you substitute b1, b2 till bk in equation 3, and also in place of b naught, if you substitute b naught equal to what? In place of x naught, we can substitute b, then we can get our expression. So what we're going to do is we'll substitute all these terms in equation 3. So we can write x of t, we can write I, the identity matrix, a t plus 1, 2 factorial, a square, t square, capital A, plus dot 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 plus 1 upon q factorial, ak, tk, plus dot dot dot. So we can take b here, b is nothing but x naught. So this is the solution of the system without control input. So this is the solution of equation 2 in the absence of control vector, control matrix. So now, what is the, so if you remember from the mathematics, what you have done before, this is nothing but the expression of e to the power at. So from this expression, we can write e to the power at x naught. So this is the Taylor series of e to the power at. So now, this, from this solution, it is clear that we can transform any value x naught to xt using the state transfer matrix. This is very, very important. So state transfer matrix is very, very useful. How we can transform from, so we can transform x naught to xt using e to the power at matrix. And this term we call state transition matrix. This is very, very powerful term. How we can transform from one state to another state using this term. This is in the modern control engineering concept, we call it state transition matrix. So now our next part is, if you take control input in a picture, how the system solution would be looking like. So let's work on this. Now, solution of state equation including the control input. Initially, we have considered there is no control input. Now we are going to assume control input. So in this equation, there was no control input. Now we are going to consider the control input into the state equation. Now, if you consider the control input here, the control input, you can write here u of t. Okay, so now we can write the state equation x dot equal to axt plus b.t. So let's assume u of t is not equal to 0, and we'll find the solution t less than greater than equal to t naught. Okay. So we'll follow the same procedure what you have done for the scalar system case. what we have done for the scalar system is, so we'll multiply both the both the terms, both side. Okay, let us define this, the equation number. This is our equation. Let's say 5. This equation 5. Let us use the equation number 6. Okay. Now, if you multiply equation 6 by a term e to the power minus 18, multiply, same procedure what you have done for the scalar system. Multiply both sides of equation 6 by e to the power minus 18, we can write e to the power minus 18 x dot minus axt equal to e to the power minus 18 but, we can write. Right. So now we know that d dt e to the power minus 18 x of t, we can write e to the minus 18 x dot t and minus e to the minus 18 axt, we can write. Now we can substitute in this expression by this term, right? So if you substitute here this term, we can write d dt e to the minus 18 x of t, we can write e to the minus 18 b is but, right? So now let us define this, the equation number 7. Okay. So here integrating equation 7 from t equal to 0 to t, we get e to the power 18 minus 18, we can write x of t minus x naught equal to 0 to t e to the minus a tau, which is the variable t to tau, b u tau and d tau, right? And from this we can write e to the minus 18 x of t equal to x naught plus 0 to t e to the minus a tau b u tau d tau. Or we can write x of t equal to e to the power 18 x naught plus 0 to t e to the power minus a t minus tau and b u t e tau d tau. Okay. So if you notice from this solution of equation, the solution of the difference matrix, which is state of the system, x of t. So you can see that here is very, very important. So in the absence of control input, we already have this system, right? This system. But if we have the control input, we are getting this extra term in our solution. So now this is very, very important here. So if we assume all the eigenvalues of A matrix are negative, we can say that the system x of t goes to 0 at time tends to infinity. We can write in the absence of u of t if eigenvalues of A are negative, x of t goes to 0 as t tends to infinity. But due to this term, it is difficult. So now, similar to the previous case, this is the term which actually making the steady state system not to track the desired values. So this is how we can find the solution of the state space system in vector case, and also we have the solution for the scalar case as well. Now we look how we can find the solution of the state space system in terms of Laplace domain. Let's work on this. Solution of state space system in Laplace domain. So here our system is x dot equal to ax plus du. So now let's taking Laplace transform, okay, question number 1 of equation 1, we can write is xs minus x naught. This is the standard formula method. If you take the time derivative, if you take the Laplace transform of the time derivative function, so this initial term will come, and a xs plus b us, right? And from this we can further write is xs minus axs equal to x naught plus b us, or we can write si minus a xs equal to x naught plus b us, or we can write from this expression x of s, we can write si minus a inverse x naught plus si minus a inverse b us. And from this we can write, please note there is important formula also for si minus a whole term inverse. So also we know that is si minus a inverse I by s plus a by s squared by s cube. This is the series power series you can write for si minus a inverse. So some formula we are directly using, but if you want to know how these are coming, please refer to some book, because if you are going to detail of it, it will take time, a lot of time. So now, if we take the inverse Laplace transform of, if we take the inverse Laplace transform of this whole equation, we can write inverse, right, Laplace transform of, let me define, this is equation, this is equation 2, equation 2, this is equation 3. Of equation 3, we can write inverse Laplace transform of si minus a inverse, we can write, so 1 upon s will be 1, because Laplace transform Laplace transform of O1 actually, so I can identify O1, O1 upon S. So if we I upon S will be, it will be I plus AT plus A square T square 2 factorial plus AQ TQ 3 factorial dot. So now we can write from this. So already we have done, if you remember, in the previous example for the finding the state transition matrix in the time domain case, what you have. So we denoted e to the power at is, this is our e to the power at, right? So similarly, we are having the same expression there also. So we can write this expression as e to the power at. So we can write SI. So this is nothing but we can say from this e to the power SI minus A inverse equal to, we can write Laplace transform of e to the power at. The same expression we can write. So this is from this explanation, it is clear that we can write this expression. Yeah. So that's why we can write from using this formula, we can write x of s, we can write x of s, we can write Laplace transform of e to the power at x naught plus Laplace transform of e to the power at b us, we can write. And if you take the time derivative of this expression, equation 4, we can write x of t equal to e to the power at, which is x naught plus 0 to t e to the power a t minus t tau b u tau t tau. So this is the solution. If we apply inverse Laplace transform, also we can find the same expression what you have done in the time domain analysis. So this is here very, very important term. The main result of this lecture is how we can find the state transition matrix, which can help us to derive the solution of the system from any initial state to any final state. And if there is control input in our system, how we can use the state transition matrix to find the solution, that as well. So let's stop it here. We'll take an example in the next lecture on how we can validate whatever we have done in today's lecture. Thank you.